رسمت بس الحادثة كانت صعبة أوي. احنا قدرنا ننقذ حياتك بس للأسف ما قدرناش ننقذ عينك.
ايه يا ابني، انا جاهز. انت فين؟ انت عارف ان انا مش هعرف انزل من غيرك.
معلش حقك عليا، حصل لي ظرف ومش هعرف انزل.
لا يا عم، ولا يهمك. في ايه؟ انا كده كده اصلا كنت مكسل انزل يعني.
آسف آسف معلش آسف.
انت متخلف، فتح وانت ماشي.
Accidents or retinal diseases can cause blindness. But does this mean that the whole visual system becomes non-functional? To answer this, let's remember how the visual system works. When light enters the eye, photoreceptors convert it into electric signals. These signals move through the optic nerve to the visual cortex, where the brain can process the info so we can perceive the world. In the case of retinal blindness, the eye is shut down, but the remaining system is intact. So what if we can replace the neurons in the eye? Visual prosthetics, or specifically retinal prosthetics, do this. Retinal prosthetics are the most prevalent in the literature. They are the most common in the market and are less risky to users because they are the least invasive. For our research, we targeted the Prima implant, which has the following features. It's a subretinal, it uses a pocket processor for real-time image processing, it's nearing the FDA approval, it has small size 2mm by 2mm, and it has limited resolution of only 378 electrodes and a limited FOV of only 7 degrees. But how does this implant actually work? Prima was designed primarily for macular degeneration. A camera captures the scene, processes it through the VPU or video processing unit, and converts it to pulses of light that are projected into the subretinal implant. This process bypasses the damaged retinal cells, and the projected lights are converted into electrical signals, which continue their way to the brain as explained before. And what does the user perceive? They perceive phosphenes. Phosphenes are dotted white lights, like the one shown here. This makes it challenging for the user to see the world, which brings us to the limitations of the prosthetics. They have very limited resolution, FOV, and no colors. Furthermore, not always continuous. Their shape can be disturbed by the axonal structure of the retina. So a main challenge now is, how can we condense a huge world of complex visual scenes into these limited prosthetics? Let's see how previous literature has tried to solve this challenge. Some worked on converting raw scenes into phosphenes directly, leading to a non-meaningful representation of dots. Others worked on processing the scene before passing it to the implant, like showing edges only or segmenting and simplifying shapes. However, they still lack the focus on what information is actually most important for a visually impaired user navigating complex environments. Moreover, the common limitation among them all, who is the core of this work? The user. These studies were largely not user-centric. There was a huge gap between user expectations and researchers' expectations. And this is where we started, letting the user dictate the design based on their needs. We began by visiting a global enterprise called Dialogue in the Dark, where employees are visually impaired and provide a real experience of what it feels like to be blind. A core component of human-computer interaction paradigms is conducting interviews with actual users to understand their needs. After conducting one-to-one interviews with 10 employees and performing thematic analysis, we found that their main challenge is outdoor navigation. What the blind actually need are two things: independence and privacy. Parallel to this, there were new directions suggested in the literature. We can summarize them as treating bionic eyes as an assistive technology rather than a vision restoration device. This means that we shouldn't try to imitate the actual eye, since hardware limitations won't allow it, but rather return to the functional vision that allows the user to do a specific task. Connecting this with the results from our interviews led us to our solution. Our pipeline is composed of 3 stages. Let's zoom in on each stage. The first stage focuses on analyzing the real scene and extracting environmental features. We primarily segment a free pass using DeepLab v3, where the user can navigate safely, and detect obstacles using YOLO v8 to help the user avoid collisions. The output of this stage is then passed to the second stage. the priority scoring and translation stage, or simply the translator. Its main function is to reduce complex object contours as much as possible by replacing them with primitive shapes and highlighting the free path with a guiding pole. But if we visualized all the detected objects on the implant, this wouldn't solve the problem of information overloading. This led us to consider object priority. Our priority equation considers the object distance, where nearer objects get a higher score. Then the highest K objects are chosen to complete the pipeline. The output is a much simpler scene that the user should perceive, which is the rule of the third stage. The third stage focuses on extracting optimized simulation values using an encoder-decoder architecture adopted from literature. The encoder output is the amplitude values needed for electric stimulation, and the decoder output is the simulated phosphenes perceived by the user. This is not a standard decoder, it's a biological simulator from the pulse to percept library. The encoder is trained in this loop to get the best optimized amplitude values needed for the safe use. Now, our system is complete. We need to validate it. Following bionic vision research standards, we used virtual reality to validate the system with sighted participants, avoiding the risk of invasive implants and the clinical trials. 15 sighted volunteers participated in our VR experiments after filtration based on inclusion and exclusion criteria, and we took their consents. The goal for each participant was to navigate the scene and reach target in less than 4 minutes and with the least number of collisions. We used our custom website, Dawn Pilot, to build the navigational scenarios. The experiment tests 3 conditions for the same volunteer. First, limited field of view normal vision, and this is our baseline for subject performance. Second, a conventional solution, and it's replicated from the literature. And third, our proposed solution. Let's see a demo of the experiment for one participant named Yusuf. The VR is set. Yusuf is now doing a practice session to become familiar with the VR. Shown here is what the researcher views, the laptop screen, to monitor the navigation both in real vision and phosphene vision. The toolkit to record and save results, and connections for all components in the system. Here is the phone view, what actually Yusuf sees in the VR. Now he started with the first condition, the limited FOV normal vision, and he's trying to reach the target. Now he is doing the second navigational scenario using phosphene vision generated by our proposed solution. Note that each condition is done twice to ensure reliability. Finally, the third condition. User now navigates using phosphene vision generated by conventional solution of edge detection. After each session, subjects were asked about pros and cons of both the conventional and proposed solutions to get their feedback. After analyzing the conducted trials using statistical methods, we found that while the number of collisions is slightly lower in the case of conventional solution, about 25%, our proposed solution achieved a lower completion time, about 17% less time. However, considering the qualitative analysis from volunteer feedback, we found that the solutions achieved these results in completely different ways. The conventional solution was not suitable for all participants. Approximately half mentioned that the scenes were clearly perceived, while the other half suffered from ambiguity and visual cluttering. For our proposed solutions, the pros were related to scene clarity and direct pathfinding, while the cons were about misleading feedback and system instability, and this brings us to our limitations. System instability was mainly due to limited computational resources, as we used our personal laptops for processing and our solution requires heavy computation due to the AI models and translator algorithms. Additionally, network instability led to some system fluctuations. Also, the guiding pole was only showing the free path without being tied to the target, i.e. not using a GPS, which causes the misleading feedback. Finally, our sample size wasn't large enough, which caused some results to be statistically insignificant. To that end, our goal was to shift the focus from attempting to restore vision to actually restoring a user's independence. And here are our key contributions. First, we conducted a user-centered survey to identify the needs of visually impaired people. Their needs dictated the design of our framework. Second, to the best of our knowledge, this is the first paper that designs task-specific solution for outdoor navigation. Third, we introduced the priority scoring and translation stage, which translates complex visual scenes into simpler priority-based language. Fourth, our custom VR platform, namely After Dawn, is open source, so researchers can use it to build VR scenarios and track experiments in easy, abstracted way.
انت كويس يا ابني.
أنا كويس، شكرا.